With all that in mind, we can actually have a brief look into our latest development on qubit structures. So the way we try to envision that is we have the qubit at the bottom layer, and on top we put the low power electronics for the control and for multiplexing. And even higher than that, also at higher temperature, we can incorporate those complex. And at IMEC, we're also focusing on two types of qubit, but they are mainly the solid-state qubit, superconducting qubit or semiconducting qubit. So for the superconducting qubit, we are looking into process development, basically try to incorporate different structures, and we are also looking into different materials, or superconducting materials, that can improve the performance. Basically, just to show the 300mm coplanar waveguide resonator development, with all those development, we can actually achieve the best-in-class single-layer process with really limited effect of the plasma damage. And we also are looking into a fab-compatible qubit platform. By optimization, basically make the qubit fabrication really compatible with the fab approach. We can actually demonstrate a T1 time or the quantum or the lifetime of higher than 100 microseconds with a control fidelity over 3.9. And on the control side, or on the multiple control side, we are also looking into RF cryogenic MUX. So essentially, we demonstrate the operation of a qubit together with the MUX, and also show that the MUX does not affect the qubit fidelity too much. Now let's switch the gear, look into the semiconducting spin qubits. So here, what we are trying to do is that we are using a hybrid fabrication process. So essentially, we are using the optical lithography plus e-beam lithography to define the feature together. That allow us to change the design very fast. We also incorporate different process monitoring structures, for example, transistors, TRM, and also Hobart. So with all those developments, we can have very good gate uniformity at millikelvin performance, and also the platform is very flexible, so we can implement either P-type or N-type qubits. So we also have looking into different structure and characterization methods. So basically, we are having different approach for the fab devices. So we have at 300 Kelvin, we are looking into the probe station, demonstrate almost 100% yield, and also very good uniformity on the threshold voltage for the transistors and also for the single electron transistors. Also, because we are making a lot of devices, we are looking into automatic ICT tuning. In the millikelvin range, the preliminary result is also very promising that we can correctly identify the best operation point automatically. We're also looking at the RF reflectometry for the readout and also the cryogenic control circuit. So here that we showed our latest result on our polysilicon MOS structures. By those optimization, we can demonstrate the best-in-class silicon MOS interface with the mobility higher than 30,000 and also percolation threshold lower than 0.8. If we measure 12 devices, and we can see very good uniformity. And then if we look into really the single electron performance by charge sensing, we can demonstrate a very good exponential control of the tunnel rate up to 100 GHz. And then we can also look into the charge noise performance, which is the limiting factor for the qubit performance. And we show that the charge noise is actually lower than 1 microeV per square root hertz. So essentially, the silicon MOS result is comparable or even better than the lab silicon germanium results. And we are also looking into silicon germanium, which would have more potential to achieve even better values.